All right, so we're starting chapter 3 today, and all of chapter 3 is concerned with applications of differential equations, specifically differential equations of the types that we've looked at so far. And then in 3.3, we'll talk a little bit about systems of differential equations. But the idea here, especially in section 3.1 right now, is to take some of the models, the mathematical models that we've come up with for different situations in section 1.3, and start looking at their appearances in specific situations like we have in the examples here, and we then want to use the techniques of chapter 2 to solve the problems that we're given. So we're kind of combining section 1.3 with sections 2.2 through 2.5, really 2.2 and 2.3, because all of the examples we're going to be looking at here fall into the category of either being separable or linear. But that's the idea. We want to use our mathematical models in applications and then solve them. Pretty straightforward. So we have 3 examples that we're going to look at today. Your book goes over several. The 3 that we're going to look at is one involving radioactive decay, one involving Newton's law of cooling, and then another one involving mixture problems. Your book goes over more, like I said, it goes into population growth. Solving a population growth problem is going to feel almost identical to how we solve a radioactive decay problem. So we're not going to do a population growth model in this section, and part of that also is because in section 3.2 we look at a better population growth model, so we'll deal with that in more depth in section 3.2. This section also talks about series circuits. We developed in section 1.3 a mathematical model for series circuits, and our model was a second order equation. If you assume that coefficient on the second order term is 0, then that reduces to a first order equation, and we can solve that. I'm not doing a series circuit example in this section today. There's no homework on the series circuit stuff, and that's primarily because we deal with the more general case of the second order equation later on in the course. So I don't really see much point in dwelling on that here. All right, that's enough talking. Let's go ahead and get into this. So our first example is a radioactive decay problem, and we're starting with 100 milligrams of some radioactive substance, and we happen to know that after 6 hours that substance has decayed by 3%, meaning 3% of its starting value, starting mass. What we want is to find the amount remaining after 24 hours. Okay, so our radioactive decay model looked like this. dA dt equals some unknown constant k times A. Okay, k is going to end up being a negative number, although you're going to see that in my approach to this problem, we actually don't even need to find k explicitly. This is an IVP because we also have an initial condition. We're told that at time 0, but the word initially is our clue there, we have 100 milligrams of this substance. So remember, the function we're looking at is A of t, which is the amount of this radioactive substance measured in milligrams. And at time 0, we have 100 milligrams. That's our initial condition. Okay. Now notice this is a separable equation. It's a very easy one to solve. Separating variables, I get this: dA over A equals k dt. Okay, using separation of variables like I did here, I would integrate both sides, and integrating both sides is going to yield this. Natural log of A equals, this will become kt plus some other constant of integration, c. Now, I'm not putting absolute value bars around this, and that's because the value A is only going to make sense if it's positive anyways. Remember, we're talking about a mass of some substance. So in the case of these application problems, it's important to pay attention to what the logical domain of a function, domain and range of a function would be. Even though, if I just think of A as some arbitrary variable, it would make sense to be able to plug negative numbers into that. Because it represents something that can't be negative, I can use that to my advantage and use it to not have to worry about absolute values here. But regardless, if we wanted to solve for A, we're going to get A equals C e to the kt. Okay, we've done this before. Again, remember this c becomes e to the c, but then I say that's an arbitrary constant and it ends up being multiplied to this. Let's just continue calling that arbitrary constant c, even though this c is not necessarily the same thing as that c. Okay, so with that done, there's actually two unknown constants here. We have c, the constant of integration, which we don't know, and then we have k, which was the proportionality constant, which we also don't know. So we basically have one equation here, but two unknowns that we're looking for. And that's the reason why we're given more information in the problem. See, even though this initial condition well, this is my initial condition from the first sentence, we actually have another point of data that's given to us. I'm going to include that up here in our original statement of the problem. After 6 hours, the substance decayed by 3%. So at A of 6. Now, if we started with 100 milligrams, 3% would be 3 milligrams, and it decayed by that amount. So 100 minus 3 is 97. Okay? So what that means is that after 6 hours, we had 97 milligrams. What I'm going to do is use both of these conditions in this function that I came up with here to come up with a system of equations in those two variables. And I'm going to use that to try and solve for something. So starting with this guy, if I plug 100 in for A, 0 in for T, that's going to give me this. 100 equals C. Now e to the k times 0 is just 1. And so I get 100 equals C. And look at that, right off the bat, without even having to use this other condition right here, I've actually managed to solve for C. So this implies that A is equal to 100 e to the kt. All right. Now, so it looks like we're actually not going to need a system of equations. But now I can plug in this other condition right here to get this. If A is equal to 97 when T is equal to 6, that looks like this. 97 equals 100 e to the k times 6. I'm going to write that as 6k. Okay? Now, what most people would do right here, I think your book does this, I think this is what you've been trained to do, is you go through the steps to solve for k. And then you can plug k back into your model up here, use it to get what you want. And that's not necessarily the wrong way to do it. I think that's fine. The issue I take with that is that k is going to end up being an irrational number. It's going to be some decimal that you have to round. And even that's not necessarily a problem, but that introduces some error into your answer. So I like, in the problems like this, I like to use a very convenient fact. Note, e to the kt is the same thing as e to the k to the power of t. I'm using a property of exponents here, that power to a power property specifically. Now, why am I doing that? Well, the reason is because instead of solving for k, I'm actually only going to solve for e to the k. This is the same thing as 100 times e to the k to the power of 6. So what I'm going to do, divide both sides by 100 first, and then take a sixth root of both sides. Or that's the same thing as taking both sides to the power of 1 over 6. What that does is it gives me this. 97 divided by 100 is just 97 1/100ths. Taking a sixth root of both sides is that to the 1/6 power, and this is equal to e to the k. Why on earth would I want to do that? Well, remember, we have this function right here. This is our solution to our differential equation up here, but we have not figured out what that constant is. And rather than deal with that constant explicitly, I'm going to think of this way. This is the same thing as 100 e to the k to the power of t. I know that e to the k is equal to this. So I'm going to take this entire thing and plug it in for that e to the k up here. Okay? That gives me this. Let's call it a of t now. A of t is equal to 100 times this, 97 1/100ths to the 1/6 power, that's going to go in for the e to the k, to the power of t. that simplifies to, I keep hitting my stand here, to 97 over 100 to the power of t over 6. You notice I haven't rounded anything yet. I haven't come up with any decimals that I've had to round to a certain number of decimal places before creating a function out of it. That means that this function is going to give me more accurate results than if I rounded something to a decimal. Maybe it's not a huge difference, but it is a difference, okay? So we've come up with our specific solution. All that's left to do is answer the question. Find the amount remaining after 24 hours. Well, that's what this function does, is it tells us how much of that substance remains after time t. So I just plug 24 directly in to my function here. 100 times 97 over 100 to the power of 24 over 6. That reduces to a power of 4. So 97 over 100 to the 4th power times 100. That goes into a calculator, obviously, and we get 88.529 milligrams. Okay? Now, like I said before, the population growth model is essentially the same approach, because in a population growth model, instead of dA dt equals Ka, we have dP dt equals Kp. So the A's become P's. It's more or less just a change in the label. Even though we're talking about a different situation, the solution will look pretty much the exact same. So that's kind of why I don't really see a point in going through a population growth model. It's not really going to be anything new for us. Let's take a look at this next problem. This is a Newton's law of cooling type of problem, and this is actually going to feel pretty similar to what we did in 3.1. Not exactly the same, but it's gonna have kind of a similar flow to it. So let's remember what let's read it first. Sorry. A thermometer is taken from inside a room to the outside, where the air temperature is 5 degrees Fahrenheit. After 1 minute, the thermometer reads 50 degrees Fahrenheit, and after 5 minutes, it reads 30 degrees Fahrenheit. What is the temperature of the room? Okay, so remember the way Newton's law of cooling works is it's a mathematical model for the temperature of an object that has a different temperature than its surrounding medium, or its sometimes we call that ambient temperature. In this case, we've taken a thermometer that's been sitting inside a room, so we're going to assume that the thermometer, before moving it, is the same temperature of that room. But then we move it outside where it's very, very cold. It's 5 degrees Fahrenheit. It's below freezing out there. The thermometer is going to cool down over time, right? And so what we seek here, before we can answer this question, we seek a function that would give us the temperature of our thermometer at any given time, T of t, capital T of lowercase t. If we can plug 0 into that, that will tell us the initial temperature of our thermometer, and the initial temperature of the thermometer should be the same as the room, so that will help answer the question. When we developed Newton's law of cooling, we came up with this model, dt, capital T, dt, lowercase t, equals some constant of proportionality, k, times T minus the ambient temperature, or the temperature of the medium. I think we call that Tm in our example. But we know that value. We're given that value here. We're told that the air temperature is 5 degrees Fahrenheit. It is assumed that the air temperature is constant out there, so that's kind of important. We also have we have an initial condition, and as was the case in the previous example, we actually have 2 points of data that we can use. We're told that after 1 minute, the thermometer is 50 degrees Fahrenheit. That corresponds to this. T of 1 for 1 minute equals 50. Remember, the output represents temperature. Additionally, we're also told that T of 5 is equal to 30. Okay, and once again, the reason why we need 2 of these as opposed to just 1 initial condition, which is usually what you need, is because in addition to the constant of integration that's going to pop out when we try and solve this, we also have this unknown constant of proportionality. So that means we have 2 unknowns as opposed to just 1. This is another separable dE. Again, if separating variables, I get dt over t minus 5, excuse me, equals k dt plus c. All right. I can integrate both sides. So integrating both sides, I'm going to get natural log of t minus 5 equals c e to the k t. Oh, sorry, I'm getting too far ahead of myself. Equals kt plus c. I jumped ahead a step there. I shouldn't have done that. This leads to t minus 5 equals, now we have c e to the kt, and adding 5 to both sides, you get t equals c e to the kt plus 5. Okay, a couple of things. First of all, once again, I did not use absolute values here, and why didn't I do that? Well, I know that t minus 5 is going to be positive. And how do I know that? I know that because the temperature of the thermometer is going to be greater than 5 degrees at any given time in this model. How do I know that? Well, we have readings on the thermometer here and here. Remember, the only thing influencing the temperature of the thermometer, once it's moved, is the outside temperature, which is 5 degrees Fahrenheit, which means it starts at a different temperature and will approach that 5 degrees. But we're seeing that at different points in time, the thermometer was 50 degrees Fahrenheit and 30 degrees Fahrenheit. It was warmer than the outside temperature initially. So that means that the thermometer will only ever be greater than or equal to 5 degrees Fahrenheit while it's sitting out there. It's not going to get cooler than that. Okay, so I'm using that to disregard the absolute values. Notice also our solution looked really, really similar to what we were getting in the previous problem. The only difference is that we added this constant here, this plus 5. And so that's kind of what separates this from like a radioactive decay or population growth model. This is the point where I have to start figuring out C and K. So that's where I want to use these conditions up here. Evaluating this function at these values, I'm going to get 50 equals C e to the k times t. In this case, t, lowercase t is 1, so that's actually just c e to the k plus 5. Okay? And then let's see. Oh, you know what? I think I have a typo on here. Let me check something real quick. I'm pretty sure my temperature was supposed to be something else. I want to make sure I fix that before we keep going so that we don't... Yes. Sorry. This is actually supposed to be 55 degrees Fahrenheit. I had written that problem down incorrectly, and I don't want that mistake to keep showing up in there, because we'll get a weird answer. Okay, yeah, sorry, that should have been 55 degrees Fahrenheit. So at 55 degrees Fahrenheit at time 1, that's what that would look like, plugging that point in here. This one is correct. So we have 30 degrees at time 5 minutes. So that means c e to the 5k plus 5 is what I'll have down here. Okay? So I know I make all these little typos in these videos and kind of sloppy. I just sort of scribble them out. Hopefully you're following with that, okay? Let's subtract the 5 for both sides in both cases. I get 50 equals c e to the k. In that case, 25 equals c e to the k. In that case, 5k. Okay, now I have two unknowns still, c and k. These are not linear equations, so I don't approach these the way that I would solve a system of linear equations. What I'm going to do in this case is take my second equation and divide it by my first. Because if I do that, on the left-hand side, I get 25 divided by 50, which is 1/2. And notice that if I do this side divided by this side, the c's will cancel each other out. And I get e to the 5k divided by e to the k, which is e to the 4k. Right? Now, as before, I don't want to solve for k explicitly. I actually want to solve for e to the k. So if I take both sides to the power of 1/4, I'm going to get this. 1/2 equals e to the k. That gives me a substitution that I can use here. Okay, so plugging, where's my 1/4? There we go. Making that substitution, here's what I get. Where am I going to write this? Let me write it down here. I'm starting to run out of space. So now my function looks like this. T of t equals, we still don't know c, right? C e to the k becomes 1/2 to the 1/4 to the power of t. That becomes 1/2 to the t over 4 plus 5, right? So at this point, what's the goal? I want to figure out what t of 0 is equal to. And we don't know that, so I need to find c before I can start plugging things into this function here. And to find c, I can use one of my other initial conditions. So let's see. Let's go back to this guy up here. If I plug 1 into my function here, I should get 55 again. Remember, at time 1 minute, the temperature is 55 degrees. So using that initial condition again, 55 is equal to c times 1/2 to the 1/4 plus 5. Okay? Notice now c is the only unknown in that equation. I can solve for c. And what's that going to look like? Subtract 5 from both sides to get 50. Divide both sides by 1/2 to the 1/4 power. So that's going to give me c equals 50 over 1/2 to the 1/4 power. Again, you notice I'm not putting anything into a calculator quite yet. Let's actually write that even a little differently. 50 times 1/2 to the negative 1/4 power. Okay? Now, kind of ran out of space. We're going to come up here. What does that let me do? Well, let me go rewrite, finally, my function using everything that I know. T of t is equal to c, which we just found, 50 times 1/2 to the negative 1/4 power, e to the kt, but notice, again, down here, e to the kt became 1/2 to the t over 4 power. 1/2 to the t over 4 plus 5. There's some simplifying that I can do here. Notice these two exponentials have the same base, so I can add their exponents. I get this, 50 times 1/2 to the t minus 1 over 4 plus 5, okay? And again, I want to point something out here. At no point have I obtained any values in this function that have had to be rounded. I like to hold off on any rounding as long as I can to minimize the amount of compounding error that I get in an answer. Eventually we have to round, but we can hold off on it. So now, what is it that we actually want? Well, we were asked for the initial temperature or the temperature of the room, which is the same as the initial temperature of the thermometer. That is T of 0. So we're almost there, guys. T of 0 is equal to 50 times 1/2. Plug a 0 in here, I get negative 1/4 plus 5. That part just goes right into a calculator. That's approximately 64.46, and remember it's in degrees Fahrenheit. Okay? So it's 2 examples in the bag. We have one more that we want to do, and it's a mixture problem. We're going to do that in the next video.